Hello everyone, I'm Rosie Lester from the CCDC, and today we're going to learn about how chemists describe symmetry. We'll start by discussing what point groups, symmetry elements, and symmetry operations are, before seeing how a point group is decided by identifying symmetry elements. We'll use a flowchart to decide what point group something belongs in, and then there's a chance for you to practice with some examples. Let's get into it. First of all, what is a point group? In the field of crystallography, a point group is a list of all the ways in which the orientation of a crystal can be changed without seeming to change the positions of its atoms. In other words, what symmetry operations can be applied to a crystal and leave it unchanged. This might seem a bit of a pointless exercise, but in 1830, a German mineralogist, Johann Hessel, proved there were only 32 distinct combinations of these symmetry operations. This means by characterizing the symmetry of one crystal or molecule, we get information we can apply to many others, because lots of properties depend on the underlying symmetry. The next question to answer is, what are symmetry operations and symmetry elements? A symmetry operation is the actual movement of a body like a molecule, such that after the movement, the molecule appears the same as before, like a rotation or a reflection. A symmetry element is a geometrical entity about which a symmetry operation is performed, such as a point, axis, or plane. Don't worry if this seems confusing. We'll cover both of them as they come up in the next section. The operations we'll focus on today are reflections, rotations, inversions, and the identity operator. Although we discussed crystals earlier, we're going to look at the effect of operations on individual molecules, so they're a little easier to visualize. You can spot symmetry elements in other objects too. Keep watching for ideas of where to find them in the world around you. Let's start with the last one on the list. The identity operator means we do nothing to our crystal, so it stays the same. This is like adding 0 or multiplying by 1 in maths. As you might have guessed, this means it applies to every object. It's included as part of a mathematical way to describe point groups and symmetry, and there are lots of molecules which have no other symmetry, such as this one. The identity operator is a bit of an odd one out, since it doesn't have a symmetry element corresponding to it. We'll see for others on the list that they all do. It is given the symbol capital E. Working along the line, we have the inversion operator. Mathematically, it is described as moving whatever is at the point x, y, z to minus x, minus y, minus z. This means every point is passed through the centre of the molecule and out the same distance from the centre that it started at. Try following the arrows to see it in action. The centre doesn't have to have an atom at it, just like in this example, and we can find it by checking where the arrows of motion intersect. The symbol lowercase I identifies the centre of inversion. The next operation we will discuss is rotation, which takes place around an axis. Rotations can be described as n-fold, where n is a number. More specifically, the number of rotations we can fit in 360 degrees. As an example, if the molecule can be rotated by 180 degrees and look the same, we call it a two-fold rotation because we can fit 2 rotations in 360 degrees. One example of this is water, but I'm sure you can think of molecules with different numbers of rotations within 360 degrees. Benzene, for example, can fit 6. The symbol for a rotation is C subscript n, where the n is the number of rotations. A molecule can have more than one axis of rotation, and they don't have to have the same value of n either. Can you spot any other axes of rotation in benzene? Pause the video to think. Well done if you found a C2 axis. Benzene has 6 of them, 3 going through atoms and 3 going through bonds. Don't worry if they were hard to spot. Finding symmetry elements gets much easier with practice. You might be wondering about a special kind of molecule, which can have infinitely many rotations around an axis. And you're right, some molecules can. Linear molecules, like hydrogen cyanide, can rotate around an axis that goes right through them, so they get an infinity sign instead of a discrete number. The final operation we come to is the reflection, and the element associated with this is a mirror plane. Reflections are familiar from real life, but here's an example of how a mirror plane looks in benzene. Mirror planes are given the symbol sigma, a Greek letter. However, they can have a subscript to help tell us more about them. An H tells us this plane is horizontal with respect to the main rotation axis, and if there's more than one rotation axis, like in benzene, we take the highest order of rotation as the most important. In this case, that's the C6 axis we found before. There are also mirror planes which include the main rotation axis. In this case, we have two separate sets. Set 1 is called V for vertical, and we can see that this must all be in one set because as soon as we find one, the rotation axis creates the other two for us. There is another set which includes the rotation axis, but we've already used up the letter V, so these get the letter D for dihedral since they intersect bonds. Don't worry too much about the letters for now. Just remember V includes the rotation axis and H does not. Others are likely to be special cases. The final thing to talk about is the improper rotation, a combination of a rotation and a reflection. This means we do the rotation as normal and then reflect in a plane perpendicular to the rotation axis, the sigma h plane. Improper rotations are given the symbol S with subscript n, which represents the n-fold rotation number. Let's use ethane as an example. It has a proper axis of rotation and an improper one, coincident on each other. What order do you think each one is? Pause the video to think. We have a C3 and an S6 axis, both shown here with a yellow line. The S6 is made from a rotation of 60 degrees, which looks like this, followed by a reflection in the plane perpendicular to our axis, shown in blue. We can see that we need the reflection to get back our original orientation, because if we stopped after the rotation, it would not look the same. The proper rotation doesn't need this extra reflection step, because we would rotate by 120 degrees in the first place to return to our original structure. We've learned about the different symmetry operations, symbols used to identify them, and the elements associated with them. We said before that a point group was a list of symmetry elements, so to identify the point group, what we need to do is identify symmetry elements in our object. To be systematic about it, we'll be using a flowchart to help us decide what symmetry a molecule has, which is also available as a PDF found in the description below. Don't worry if you haven't got everything memorised, you can always go back to sections of the video. Let's have a go with some of the molecules we've seen this far. Pause the video before each example to have a go at deciding the point group for yourself. First, we'll look at hydrogen cyanide. It is linear, but it doesn't have a centre of symmetry, making it C infinity V. Next, let's do water. Water is not linear, and its highest order of rotation is just 2. It does have a C2 axis, but that is the principal axis and there isn't one perpendicular. It has a mirror plane which contains the symmetry axis, so no sigma h, just a sigma v. This makes it C2V, where we've used n equals 2. How about bromochlorofluoromethane next? Like we said earlier, it has no symmetry elements other than the identity, so this is nice and simple. We just follow all the no's until we reach C1. Now let's work out ethane. Ethane is not linear, and despite having a C3 axis, there's just one of these. It has 3 perpendicular C2 axes, no sigma h, and 3 sigma d's, making it D3D. If you're having difficulty spotting the C2s, Think about an axis going through the centre of the molecule at an angle which peaks out exactly between the hydrogens when viewed from the end. Finally, let's think about benzene. It isn't linear, and it only has one C6 axis, and no other axes of a higher order than the C2s we found before. Its C6 counts up here though, and we know it has perpendicular C2s and a sigma H, making it D6H. Well done for making it to the end of this video. Today we've learned what a point group is, been introduced to the identity operation, the inversion operation, reflections and rotations, remembering that an improper rotation combines rotation with a reflection in a perpendicular mirror. We learned the symbols for the elements associated with these operations, and we practiced identifying them to assign point groups to molecules. The next step is to explore what symmetry exists in crystals when molecules pack together in repeating patterns. If you'd like more practice, why not try spotting symmetry elements in the world around you? Flowers, flags and tiles are great places to start. Or head to the description for some other resources to extend your learning. Don't forget to like the video and follow CCDC for more short educational videos.